In this video, we will study the circuit constraint. It's a very important constraint for modeling vehicle routing problems. Let's see how it works. The circuit constraints use as decision variables the successor array of variables. So this is the successor arrays, and these are the corresponding indices. The successor arrays tells you for each city what is the next city that you will visit just after this city in the corresponding index. So let's take, for instance, the city at index 0 and see what is the next city that we need to visit. So at index 0, the next one that needs to be visited, we just need to see in the successor array, that's the city number 2. So we will move to that city. And after the city at number 2, what we need to visit is the one at index 1, so we go there. After the city 1, we move to city at position 4, which is this one. After the one in position 4, we go to the city at index 3. Which is this one. After the city at index 3, we go to city at index 5, and then we close the circuit and come back to the city at index 0. So clearly, we can already observe that all the successors must be different. If it's not the case, you will visit 2 times the same city, and that's not allowed by the circuit constraint, because the circuit needs to be what we call Hamiltonian. But that's not enough. We must also enforce that we have no sub-circuits. Let's see how this might happen, although we have all different successors values. So this is an array of successor values, and as you can see, they are all different. Nevertheless, we are violating the circuit constraint because we have 2 sub-circuits. We see that we have one sub-circuit that is represented here with this color, and we have in green a second sub-circuit that is also looping on itself like this. And so that's not allowed. A Hamiltonian circuit has just one unique circuit. So we also need to do something else than the all different constraints to filter the circuit constraint. As a first application for the circuit constraint, I would like to show you how to model the traveling salesman problem using the circuit constraint. As input, we receive the distance matrix between any pairs of cities in our TSP. We create the solver, and then we create the variables for the successors. You see that the domains for the successors are from 0 to n-1, because we need to have a permutation there of all the cities. Then we will compute there for every city what is the distance to the next city. This is what will be captured here, and we put a large value like 1000 to say that the distance to the next city is less than 1000, and that's enough for this small demo. Then we post the Hamiltonian circuit constraint. And of course, we need to make sure that these entries in the distance of the successor is correctly computed. And so for that, we use element constraint. The element constraint will just here take one row of the distance matrix, that the row number I, okay? And so the row number I gives you for every other cities what's the distance to the other cities, and the one that needs to be stored in the districts of I is the one that corresponds to the next city that you will visit, okay? And so this is why we capture correctly the distance to the successor there. Of course, we need to collect all the distances to the successors, and therefore we use the sum constraint there to compute the total distance. That's our objective function, so we want to minimize this, and we create the depth first search to start the search, and you can use, for instance, a first fail strategy to make it a little bit more efficient. So that's very convenient to model the traveling salesman problem using circuit constraint. But you can also model a little bit more complex problems like vehicle routing. And for vehicle routing, you typically have more than one vehicle. So here I have represented a unique depot, and you will have 3 different vehicles that are departing from the depot and visiting a set of customers. But the set of customers that you need to visit is not fixed. So it's not clear that the green vehicle, the red vehicle will visit exactly this amount of customers. Maybe it will be less, maybe it will be more. Okay, and so that depends of what you want to minimize and what's the problem instances, of course. But the goal here is to model this problem with just one unique circuit constraint. And that's not completely trivial, because the circuit constraint does not allow to come back to the depot, because you should visit exactly once each city. So if you consider the depot as one city, you should not visit it 3 times, as it's the case here. So we have a small modeling trick that we use for modeling with one unique constraint this problem, is this one. We will duplicate 2 times the depot, and so we have 3 depots. And we will virtually color the depot to represent the truck that is starting from that depot. And with verified constraint, you can also model the visit of each city to exactly capture which truck visits each city. And so you post just one unique constraint and you can have it Hamiltonian here because every city is visited exactly once. And of course, the distance between the depot themselves, between this virtual depot, you should set it to 0 because you don't want to increase the tour length because of this modeling trick. The Hamiltonian circuit problem is an NP-complete problem. Okay, for general graph, it's NP-complete to decide whether a circuit, Hamiltonian circuit exists that visits each city exactly once for an undirected graph. And that's a very bad news for us because what we would like to do is filter the Hamiltonian circuit constraint. And so as a reduction to prove that it's also NP-complete to achieve domain consistency for that constraint, we can, it's quite straightforward to make the reduction. Okay, we make the reduction of the filtering to the Hamiltonian circuits problem. We will introduce for that reduction one successor variable for each node in the set of vertices of your graph, input graph, and the domain of that successor is simply all the nodes that are accessible with just one edge visit, okay, with just one edge used in your input graph. Okay, so the domain of the successor of I is all the outgoing nodes from the node at index I. And so if you apply the domain consistent filtering algorithm on this encoding of the Hamiltonian circuit, on the circuit constraint there, on the successor variables that we just have created, then you can have 2 possible outcomes. The first one is that the circuit constraint tells you, yes, there is no failure. And if there is no failure detected by the domain consistent filtering algorithm, you can clearly answer, yes, there is an Hamiltonian cycle in my original graph. And if the domain consistent filtering algorithm tells you, no, there is no Hamiltonian, there is no solution to that constraint, then you can say, you can conclude that there is no Hamiltonian cycle circuit also in the input graph. And so that's a bad news because it means that domain consistency for that constraint is NP-complete. So what can we do there? Clearly, we will not be able to do domain consistency cheaply. That would be very costly to achieve, and we don't want to do that in a propagator that is called many times in each node of the search tree. Instead, we will use a relaxation of the filtering, and that will be the topic of the next video to show how we can relax a little bit the constraint to do some useful filtering for the circuit constraint.